Hello everyone, my name is Cameron Brown. I'm a research fellow for the CMAC Future Manufacturing Research Hub, and today I'm going to talk to you about some of the work we've been doing in the use of particle vision tools for the monitoring of agglomeration during crystallization processes. So to set the scene here, what is agglomeration and why might it be a problem? In general terms, agglomeration is the clustering of small objects into a single mass. And in terms of crystallization, this might involve single crystals clustering together to form more complicated particles. Now this can cause a number of problems during downstream processing, as the product we produce might not be consistent or stable. And we can also have entrainment of mother liquors between the particles, which remains after filtration and drying, resulting in reduced product purity. Now there are a couple of strategies possible for dealing with agglomeration. We can look for process conditions which agglomeration does not occur, and this could include looking at the impact of process parameters such as solvent type, mixing regimes and seed type. On the other hand though, if we're happy with forming agglomerated particles, we might do nothing about them as long as we can produce them consistently. For this talk, I'm going to mostly talk about how we identify process conditions to avoid agglomeration and how particle vision tools aid in this. So if we're looking to design the crystallization process, when might we be interested in finding out if agglomeration is a problem and how can we make changes to prevent it? What we've shown here is a workflow approach to the design of continuous crystallizations, and this covers aspects from solvent selection through to process design and execution of a large lab or pilot scale crystallization. Now if we discover agglomeration is a problem towards the end of this process here at stage 7, it's really too late to make significant changes to the process design, and certainly won't be able to change any solvents. However, earlier on in the workflow, when we're looking at the first stages of process design, if we find agglomeration, it might be possible to deal with this and design it out through mixing regimes and agitation rates. However, ideally, we'd like to know if agglomeration is going to cause a problem as early as possible, and for example, when we're looking for suitable solvents. So how do agglomerates form and what parameters might we be able to change to influence this process? So shown here is the schematic of agglomerate forming process, which takes place in 3 stages. The first step is the collision of particles together, and then this is a function of the number of particles present, the size of these particles, and the hydrodynamics of the crystallizer in use. Now once these particles have collided together, they must be held together for sufficient time for stage 3 to occur. And in stage 3 is the growth of bridges between these particles to cement them together. Now at any stage, disruption can occur, leading to the breakage of the particles and reversing the agglomeration process. And then just to clarify before I move on, I'd like to talk about the terminology I'll be using in this talk, as the definitions do vary. So here I'm classifying an aggregate as a particle which has only undergone the first 2 stages, and whereas an agglomerate has undergone all 3. Now this inherently means that an agglomerate is stronger and more difficult to break than an aggregate, and also it can only occur under supersaturated conditions. Now based on this mechanism, we can identify the levers or process parameters which govern agglomerate formation. The work I'm going to talk about today will focus on interparticle forces through solvent selection and collision rate through crystallizer design and agitation rate. Before we get too far into investigating these process parameters, we need a method for monitoring agglomeration. Now ideally this method must be in situ, as filtering and drying samples could induce agglomeration. Now visually it's very easy for a person to distinguish between a single crystal and agglomerate as they have distinctly different shapes. However, classifying thousands of particles manually would be very time consuming and wasteful. Now this is where particle vision tools come into their own and provide automated methods for the identification and description of particles. Now I'm not going to go into too much detail about the various methods available, but these can range from simple thresholding techniques to machine learning algorithms. And the particle descriptors calculated give an indication of the particle shape and can change during an agglomeration process. So for example, in the graphs in the bottom left here, we see the change in the distribution of particle circularity with time for 2 different solvents. Now this is where a high circularity would indicate more single crystal-like particles. Now for a non-agglomerating solvent such as ethanol, we see that the mode of this distribution does not change significantly in this time. But for something like acetonitrile, where we see large agglomerates forming in images, we see a drastic shift in the mode of this distribution. To cover the experimental work I'll talk about in a second, I've summarised here the various tools used in the study. For our crystallizer, we're using an EasyMax platform at the 100ml scale with a range of different impellers. And although we're monitoring the process with our wide range of PET tools, for this talk we're only really interested in the PVM probe. I'll talk about the effect of mixing later, but to quantify this we've developed a CFD model for the crystallizer, including all the various PET probes. Now the basic procedure for this study is to perform seeded crystallizations of paracetamol with previously characterised seed and a couple of additional constraints. We'd like any significant change in the particle size to be due to agglomeration, therefore high seed mass is used to minimise growth. However, the mass of particles was limited to 1 weight percent to ensure clear imaging of the particles without any overlap. And for the image processing, we've used a relatively simple thresholding technique implemented in MATLAB. So on to some experimental results. Shown on the right here are sample PVM images of the particles in a range of solvents. And qualitatively, looking at these images, we could say that acetone and MEK produce large agglomerates, followed by methanol and ethanol, with 2 propanol and 1 butanol producing particles which look similar to single crystals. Now, can particle vision tools give us more information, however? So firstly, we can see that not all shape descriptors will vary with the agglomeration process. For example, slenderness here shows no difference between the non and agglomerating solvents. We can, however, see that circularity and circle equivalent diameter change with time and give different responses in different solvents. We see rapid agglomerating solvents such as methanol, acetone and MEK, which have a sharp change in circularity and CED within the first 2 to 3 minutes. On the other extreme, we have 1 butanol and 2 propanol, which show very little change in particle size and shape, suggesting no agglomeration is going on. Then in between these two, we have ethanol, which agglomerates but takes its time about it. So as all other experimental conditions were as equal as possible, what are the underlying properties of the solvents which could be causing these differences? In previous work, viscosity and solvent polarity have been shown to correlate with the degree of agglomeration. Now these represent 2 different aspects of the agglomeration forming mechanism previously described. Now, viscosity affects the hydrodynamics of the crystallizer and therefore the collision rate of particles, whereas polarity represents the interaction between solvent and particles during the second stage of agglomerate formation. Now for the experiments performed in this work, we can see in the bottom right here that we have a clear correlation between the viscosity, circularity and particle size, but the trend is not as clear when using a measure of polarity. If in this case that polarity is not suitable for describing the solvent property influence agglomeration, can we identify others? So shown here are commonly available solvent parameters, and we've used these parameters to build a partial least squares model between the parameters themselves and the final particle circularity and size. Now after refining the model to maximise the fit, we're left with a range of parameters shown on the right hand side here, which really are dominated by hydrogen bonding effects. Now this is perhaps unsurprising, as it's previously been shown that the faces of paracetamol crystals are also dominated by hydrogen bond accepting and donating functional groups. So delving deeper into specific parameters, we find that one of the Snyder parameters and viscosity correlate well with the final particle circularity and size. And if we plot these out for the solvents investigated, we can see that solvents with high viscosity and high Snyder parameters lead to conditions where we have little or no agglomeration. And qualitatively, this matches what is seen in the PVM images, with acetone and MEK showing a larger degree of agglomeration compared to 2 propanol and 1 butanol. And although this works for the solvents already investigated, can we use this to predict how other solvents will behave? Now, ethyl acetate and acetonitrile with their low viscosity and low Snyder parameters would be expected to be strongly agglomerating. And in contrast, isopentanol would be expected to be non-agglomerating. And in testing out this hypothesis, we do indeed see the formation of large agglomerated particles in acetonitrile and ethyl acetate, but no agglomeration in isopentanol. You'll also notice that the image for isopentanol is not taken from a PVM probe, but from an in situ camera as part of a high throughput screen device, and this is an aspect I'll touch upon later. And now that we've considered the effect of solvent, what can be done with mixing additions on influencing agglomeration? Now looking back at the previously screened solvents, we saw that ethanol was interesting as it agglomerated but over a longer period of time compared to the others. Now this maybe gives us an opportunity to affect the agglomeration process within this time period. So here we've taken the same experimental method as before, but investigated a range of different crystallizer configurations. And these were designed as such that the average bulk shear for experiments N21 in black and N23 in pink were the same but for different stirrer diameters. and this was achieved through altering the stirrer speed. Similarly to this, experiments N13 in red and N24 in green also have the same average bulk shear, but at different crystallizer scales and stirrer diameters. Now, if we use the particle responses from the vision tools, we can see that the response in circularity and CED for experiments N21 and N23 in pink and black here are very similar, as are those for N13 and N24 in the red and the green. And again, this isn't too surprising, as shear rate has long been linked to agglomeration rates. With increasing shear, we increase the probability of particle collision, but we also decrease the efficiency of these collisions. As a result, the agglomeration rate will pass through a maximum with increasing shear. However, for the work here, we're operating at levels of shear that are past this maximum. But how effective is the bulk shear at predicting scale-up behaviour? Shown on the right here is how the final particle circularity varies with bulk shear rate. The fit in red is only to the experiments at the 100 milliliter scale, and comparing the response of experiments performed at 700 milliliter scale to this fit, we see that they also fit along this trend. Now, this does suggest that the average bulk shear is a suitable parameter for scaling up or transferring agglomeration processes. But does this control over agglomeration with mixing conditions apply to other solvents as well? Here again, we've taken the same experimental method, but using acetone as a solvent, which we've already identified as having strongly agglomerating behaviour. And although we see some changes in the final particle size, the particles are always agglomerated and end up with the same circularity by the end. And this is regardless of the mixing conditions applied. Now, this suggests that the solvent surface interactions can be strong enough to overcome any of the hydrodynamic forces that are present. Now, it should also be highlighted here that the same bulk shear rate still produces the same responses as experiments N26 and N28 in black and pink here respectively produce the same response in terms of particle size. Now, just to wrap up this work around agglomeration behaviour, we've demonstrated that we can track agglomeration behaviour through a relatively simple image processing technique. And through the tracking of these agglomeration responses, we've identified 3 different agglomerating behaviours. Now, we have solvents where agglomeration is rapid, but is not affected by hydrodynamics and mixing conditions, and this is the case for things like acetone. We have solvents where agglomeration is slower, but we can disrupt the process with our mixing conditions, as was the case with ethanol. And then we have solvents where agglomeration doesn't occur, such as 2-propanol. So just to mention as well some future work and some other considerations with this agglomeration map that's presented here. Now, this is only part of the story, as it has no input from particle properties. And now this is important as with evidence that shows that seeds crystals produced from different sources can influence their agglomeration behaviour. So for example, particles that are produced through dry ball milling behave very differently to those produced through wet milling. Another thing to consider as well, that the parameters we've identified here in terms of viscosity and Snyder are very specific perhaps to just paracetamol. So we're looking to broaden the study and identify parameters which work across a range of different APIs. So finally, I'd just like to highlight some other areas where we're using particle vision tools as part of a crystallization process development. Now, laser diffraction is a fairly common used technique for particle sizing, and if we're doing a wet dispersion, we need to have careful selection of that dispersant as to ensure that the particles that we're measuring are representative of them in the process. Here we can see particles from the same batch which have been suspended in 2 different dispersants, and you can see quite distinctly here that dispersant 2 is producing a much larger PSD compared to dispersant 1. Now, if we relied on laser diffraction measurements by themselves, we might assume this is due to batch variation or some other changes within the process. However, looking at in situ imaging here, we can clearly see that dispersant 2 produces much larger agglomerated particles compared to dispersant 1. And then this is something you wouldn't be able to pull out without this imaging methodology. And lastly here, I touched on this previously, but we're also looking at acquiring images from other sources, not just PVM probes. So here we've got images taken from an in situ camera on a high throughput screening platform at the 5mm scale. And again, the idea behind this is, can we get similar responses to that what we get with the PVM probe, but at a smaller volume? And finally, just to close, just some acknowledgements for those that have conducted and supervised this research. I'd like to also thank CMAC and APSRC for funding this work, METTLER Toledo for giving me the opportunity to present today, and obviously for your time today as well. Thank you.